Hello and welcome you all to another session on line commutated and PWM rectifiers. Today we will talk about Clarke and Park transformation. Um, so in the course structure and the content, we are roughly in the 4th week and we are going to cover this part of the course. Okay, and this information or this knowledge will be useful in the subsequent week or in the subsequent uh, chapter on DQ modeling and small signal analysis. Now this is the content, Clarke and Park transformation, and we will do the power calculation with the help of Clarke and Park matrices. Yeah, so before I do this one, so let me just summarize that we have talked about space vectors, and where we understood that the three-phase quantities can be represented by a space vector, which can be described both at the steady state as well as at transient conditions. Okay, and space vectors have a particular magnitude and an angle. The discussion that we are going to cover today is will build upon the space vectors. Okay, we will do power calculations based on these concepts, but this subject is a slightly advanced. We do not generally cover in the BTech or bachelor's level, and that's why the color of this slide has been kept orange, just to show that okay, this is slightly going towards the master's level. Okay, so just to recall, we had covered this in the previous week. How we define space vectors? As you can see, the space vectors of voltage, the space vector of voltage and the current are shown here, which is VA, VB, VC with this multiplying factors and a 2/3 factor at the beginning. Okay, so the individual voltages, currents can be balanced, unbalanced, and need not to be sinusoidal. Okay, so we can have harmonics inside this also. So this is what a space vector is defined. And for example, this is an example. So if you see a balanced condition with currents in the three phases, time varying currents, Im cos omega t and cos omega t minus 2/3 and cos omega t. So if you do this and if you put it into the formula, okay, we get that the IABC is having a particular amplitude which is equal to the peak value of the current, and then it has this e to the power j omega t. Okay, so the resultant current space vector has the same amplitude as that of the peak current and rotates at the same speed. So you can see this is the rotational speed omega here. Okay, this is the rotational speed of the space vector. Okay, so now what we will see here, so this is kind of like an observation or an animation. Okay, this is an animation which shows how space vectors can be observed from different reference frames. Okay, so suppose I am standing on this axis. Okay, this is the A phase axis. Then I can say that the projection of this, so I'm standing, so this is the stationary axis, which is the A axis, and this one, the light blue one which is rotating, okay, that is the space vector. Okay, so if I can just stop it, okay, I cannot. Okay, anyway, so if I observe it here, okay, then I can see that at the point, okay, so here you can see the resultant space vector. The resultant space vector is here, okay, which you can see this light blue color, right? And I have stopped it, and then again I can run it. Yes, you can see here how the space vector is rotating. But here what is important for you to understand is that for example at this point here, what is the projection on the A, B and C axis. Okay, so basically when the space vector is rotating, as you can see, there is a projection which is happening on the A axis, B axis and C axis, and that projection is obtained here, okay, at this position. Okay, so with this actually you can be able to know that, okay, when you observe it from different reference frames, okay, when you stand on the A axis, okay, so suppose you stand on the A axis, then if you stand on the A axis, then you are here and you are basically seeing what is the projection on this A axis, okay, right, and this projection can be obtained here. Okay, you can see how much is the A phase projection and like that. So this is the space vector which is observed from the ABC axis, right. Now this space vector, the resultant current space vector, has a real and imaginary component, right, which are time varying and oscillating in nature. As you can understand, it has a real component and a imaginary component, and these are given by this I alpha and I beta, okay, which is the real and imaginary component of the space vector. And of course if you do the mathematics, it will come out to be something like this, okay, just putting it the values which are shown in this equation. Now so which means now we have basically real axis and an imaginary axis, and we are terming, or we are giving a new name for these axes, that is alpha axis and beta axis, and these two axes are stationary, okay, and they are displaced by 90 degrees. So how will they look like? Okay, so if you see here, then this is how it will look like. Again, you can see here, this is the alpha axis and this is the beta axis, okay, and the resultant space vector, that is the light blue colored space vector, is rotating, and we are observing its projection, right, and you can see here that here we can see what is the projection at any instant of time. Okay, now here one of the things you should note is that the beta axis is leading the alpha axis in space, okay, by 90 degrees, but if you see the projection, the I alpha, okay, the value of I alpha is going to lead the value of I beta by 90 degree in time. Okay, so if you see here with respect to time, okay, you will see I alpha is here, okay, and I beta is 90 degree lagging. Okay, this will be I beta, but in space, okay, in space alpha axis is leading the beta axis, alpha axis is lagging the beta axis by 90 degrees. Okay, and so this is the relation between the space axis and the time axis. Okay, so this you should observe, right. Now going back to this one, so we see that I alpha and I beta are, if you observe it from two stationary axes which are displaced by 90 degrees, then we can see that they are sinusoidally varying with time. Okay, right. Now for a more general case, suppose we take a 3-phase 4-wire system where IA plus IB plus IC is not equal to 0, then we define the I0, okay, I0 is the zero axis component of the current, and this is given by 1/3 IA plus IB plus IC by definition. Okay, so I0 is defined as 1/3 of the sum of the three quantities. In a balanced case, this is equal to 0, but in an unbalanced case, this is not equal to 0. And so if you have this I alpha beta 0 and put these values here, you can write it in a matrix form. This is the matrix form, okay, where you can see this is the IA alpha beta 0 and this is the IA IB IC, and they are connected with each other through this matrix which is given here. And this matrix transforms ABC variable into alpha beta 0 variable, and this is called the Clarke's transformation matrix, which we are giving a name TC. Okay, TC is the Clarke's transformation matrix converting ABC quantities to alpha beta 0 quantities. Okay, so this is how I alpha beta 0 will be looking like. Okay, in a similar way, you can also have the inverse Clarke's transformation matrix, right, and which is TC inverse. Okay, and if you do the matrix operation for these variables, you will find TC inverse is something like this. It converts the alpha beta 0 variable into ABC variables, right? So this is the first part of this transformation, Clarke's transformation matrix. Okay, and this is the visual representation of the Clarke's transformation matrix, and the ABC and alpha beta 0, ABC and alpha beta usually lie at the same plane. Okay, yeah, so ABC is here and alpha beta is in this plane, and 0 is 90 degrees. 90 degrees to the alpha beta axis. Okay. Yeah, in case of balanced system, the 0 component in alpha beta have a 0 value. So just to summarize this one, so usually what happens is this is the alpha axis and here is the beta axis. Okay, and this angle is 90 degree here, and this is the 0 axis which is perpendicular to the plane. Okay, so this 0 axis here is perpendicular, so this is the plane here. Okay, this is the plane, so you have to assume that there's a 3-dimensional plane. Alpha and beta are on the same plane while 0 is perpendicular to the same plane. Usually what we say here is that ABC lie on the alpha beta plane. Okay, so yeah, so in case of a balanced system, the 0 component in alpha beta 0 axis have 0 value. Okay, yeah, in case of unbalanced system, all components remain, right? Now, so this Clarke's transformation matrix is, again, as you can understand, there is a 2/3 factor which again comes like the definition of the space vector, and this is called the magnitude invariant transformation. Okay, so once you convert the ABC into alpha beta 0, the peak of the current in the alpha beta will remain same as the peak of the current in ABC. So for example, if IA, IB, IC are given as with Im sin omega t and Im sin omega t minus 2 pi by 3 like that, then when you transform it into alpha beta, then the I alpha will also have the peak as Im in case of balanced systems. Okay, so this is because of this 2/3 factor. Okay, and so the magnitude of the variable remains the same, or the amplitude remains the same. On the other hand, there is some authors use another form of Clarke's transformation, okay, which keeps the power same in both ABC and alpha beta, but then they will use a different multiplying factor of root over of 2/3. Okay, and this is called power invariant transformation. So here the powers remain same, but the magnitude will change between ABC and alpha beta. Okay, so we will not use it. Some authors use it because those who work more into with the power, they want to keep the power same. It's the same thing, only a multiplying factor that comes into the picture. So in this course, we will use the magnitude invariant transformation. Okay, we will use this as the Clarke's transformation matrix. Okay, so now what is the instantaneous power? Okay, so instantaneous power in a 3-phase system is basically the product of the voltage and the current that you can see here. It is the product. Okay, so similarly, the instantaneous power in alpha beta 0 variable can be also obtained in a very similar way, right? So P3 phase, which is instantaneous power, remember this is instantaneous active power. Okay, rather cut this out, this is instantaneous power. Okay, so VABCT is this into this, okay, right? Writing it in the matrix form, and then I substitute the I convert through Clarke's transformation matrix to ABC to alpha beta, okay, and then I write this one, okay. So this equation number 4 shows the magnitude of instantaneous power in alpha beta 0 variables, okay. Now here you can see there is what we see here, we get a 3/2, right, and this has come because we have used a magnitude invariant transformation. If we had used power invariant transformation, this factor 3/2 would have vanished, okay, then the powers would have been same. But now we have used a magnitude invariant transformation, and so this 1.5 or 3/2 comes in the between the two systems, alpha beta 0 and ABC. Okay, of course under balanced case the 0 components are 0, and therefore the instantaneous three-phase power is becoming like this is the equation of the power in alpha beta. Okay, so here one of the, you can now see that there is one advantage that is coming up. Now instead of if you do this transformation, instead of continuously, instead of using 3 variables continuously, we are now going to use 2 variables continuously. Okay, we will only deal with alpha beta variables, alpha voltage V alpha V beta and currents I alpha I beta, okay, rather than VA VB VC and IA IB IC. So there is a reduction of the variables in case of balanced system. Okay, that is one advantage of using this one. There are several other advantages which I will go on, which I will tell you as we go on. Okay, so again considering a balanced system, we can see that VA equal to VM sin omega t, and VB is like this and VC is like this. Okay, so now considering a capacitive load, suppose, so this is an example, we are taking an example, suppose IA is Im sin omega t plus 5, okay. So I am taking a capacitive load, the current is leading the voltage, and IB is this and IC is this, again a balanced system. How will I find out what is the active and reactive power? Okay, so not reactive power, how will I find out what is the active power? So then V alpha t is just putting it this one, V alpha is Vm sin omega t and V beta is minus Vm cos omega t, right? We are putting it into the Clarke's transformation matrix, and therefore we get this value. Similarly, I alpha and I beta, we get this one, okay. And let us multiply, and we have already got this power formula, instantaneous power, okay. And then we see that this instantaneous power under balanced case, when you put this, we have doing the calculation and you will get this value, okay. And this is equal to 3-phase active power, okay. So we say that the instantaneous power which we calculated with the help of the alpha beta quantities at steady state with a balanced system is equal to the 3-phase power, okay, 3 V RMS I RMS cos phi. This is an observation that we get, okay. And so expanding this one, okay, let us try to find out what is the reactive power, okay. So now we will go and define the power in alpha beta variables in a slightly different way, and this definition is found, I mean we are now defining something called as instantaneous complex power, because we found what is the reactive power. Now we want to go and see what is the reactive power. So instantaneous, so we are defining as something called as instantaneous complex power, okay. What is this instantaneous complex power? This is this ST is 3/2 V alpha beta 0 times I alpha beta 0 star, okay. Star is the complex conjugate, okay. So you have to recall that in many of our first course on power system, we say that S equal to 3 times VI star. Okay, and this is again based on the fact that if this is the voltage and this is the current, I star becomes like this. Okay, and when you have I star like this, we assume that for an inductive load, this is the P and this is Q. For an inductive load, P and Q are positive, and that is why we have defined it as 3 VI star. Okay, if you do this one, then both P and Q will come out to be positive, right? So similarly here also we are basically defining the complex power as 3 by 2 V alpha beta 0 into I alpha beta 0 star. Okay, now suppose the zero sequence currents do not flow, then I0 is equal to 0, and then you put this quantity here. Although V0 is present, but it will not, because I0 is not there, so it will not have the impact on the ST. So 3 by 2 V alpha beta into I alpha beta star, and when you expand it, you will see that you will get an equation like this. Okay, where you have 3 by 2 V alpha I alpha plus V beta I beta plus J. So there is a real part here, okay, and there is an imaginary part here, as expected, because now we are going to deal with complex power. Okay, so ST is the instantaneous complex power. So it has a real part and an imaginary part. So let us see what is this real part. This real part, which we are writing as instantaneous active power, okay, is given by this equation, which is basically what we had seen earlier, 3 by 2 V alpha I alpha plus V beta I beta. And there is also something called as instantaneous reactive power, okay, which is 3 by 2, that is the imaginary part, V beta I alpha minus V alpha I beta. Okay, now these two definitions, again I am pointing out, these two definitions is they are both, okay, they are valid both during transient and steady state. So you have a time varying quantities here. Okay, so now we are defining power not as like something which we obtain after one cycle. Okay, this is one of the advantages of calculating power instantaneously. This is instantaneous active power, instantaneous reactive power. Okay, and this is very useful in particular for implementation cases where suppose you have a DSP and you want to quickly find out what is the power flowing in the circuit without having to wait for the whole cycle to complete. And so we will use this kind of quantities, PT and QT, instantaneous active and reactive powers. And so these are the quantities, okay, instantaneous complex powers like this. Okay, so this is some definition. So ST, PT and QT are called instantaneous complex power, instantaneous real power and instantaneous reactive power. Okay, the instantaneous real power, okay, that PT is same as the instantaneous three-phase real power flowing in the ABC system. However, this instantaneous reactive power in alpha beta frame is something which is actually a new quantity. Okay, there is a huge amount of literature available. Okay, and because this instantaneous reactive power concept was first proposed by Professor Akagi from Japan, okay, way back in 1984, and from that point onwards, or even before that also, there was a lot of literature available on how we define reactive power and how this instantaneous reactive power, what is the physical meaning of this one. So this instantaneous reactive power under balanced case is basically equal to the three-phase reactive power, but it has a completely different meaning because it depends on orthogonal quantities. Okay, two orthogonal quantities, V alpha, V beta I alpha and V alpha I beta. Okay, we will not go into the more theoretical discussions on it, but we will rather use this as the definition of the instantaneous reactive power in the alpha beta domain. Okay, so if you substitute with the example that we discussed, okay, that this example, if you substitute, okay, the P and Q, okay, what we see here is that P is equal to 3 VRMS IRMS cos phi and Q is equal to minus 3 VRMS IRMS sin phi. Okay, which, so the minus sign is arising because we had taken a capacitive load. Okay, and that for a capacitive load we know that the reactive power will come out to be negative. Okay, right. So reactive power is considered to be positive, absorbed, reactive power absorbed. Okay, so now here is the QT. So now what do we observe here? The instantaneous active power is equal to the conventional active power under balance case. As you can see here, this instantaneous active power is equal to, so PT is equal to P, which is equal to 3 VRMS IRMS cos phi, right? The instantaneous reactive power is numerically equal. This is very important. Is numerically equal. The values are equal to conventional reactive power under balance case. Okay, so under so conventional reactive power theory defines Q as 3 VRMS IRMS sin phi. Okay, and this was defined as a component of instantaneous active power. Okay, this was defined. If you go back to the definition of what is reactive power, you will see there is one component which is in phase and one component which is in quadrature. Okay, and that quadrature component has an average value to be 0. Okay, so that is how the conventional definition of reactive power was developed. On the other hand, this instantaneous reactive power, this is an instantaneous quantity which under balance case is numerically equal to conventional reactive power. Okay, it arises because of the interaction between line voltage and currents with the other phases, and there is a lot of literature available on what is the exact physical significance, okay, of this instantaneous reactive power, but we will not go into it, and we will see that this instantaneous reactive power is a very useful quantity which can quickly give us the value of the instantaneous reactive power flowing into the system. This is very useful from implementation point of view, for example in a DSP based microcontroller. Okay, now, so we are now saying that we have understood what is this Clarke's transformation, what is how powers, instantaneous active and reactive power are calculated in the alpha beta domain. Okay, now we will now go into what is known as a DQ system. Okay, yeah. So here what we will see is something which is a little bit different from what you have already for example, alpha beta is a little relatively easy to understand. DQ is slightly you have to visualize it. Okay, so now here a rotating space vector. So let us go back to the rotating space vector. As you have seen here, there was a rotating space vector, say I. Okay, this is rotating here, and we said that we have this A, B, C axis through which we can see the vector. We also have this alpha axis and the beta axis which is here, and we can stand here and observe the rotating vector. Okay, so we can actually observe the same vector, okay, from different reference frames. Okay, so if suppose we observe this current vector, this I, from the ABC reference frame, then we use the terminology IABCT. Okay, suppose we observe the same rotating vector from alpha beta 0 reference frame, then we say I alpha beta 0, again a function of time. Okay, space vectors are always function of time. So the same space vector I, okay, when I observe from ABC reference frame, we say I ABC. When I observe from alpha beta 0, I say I alpha beta 0. Okay, now note that alpha beta 0 reference frame can be anywhere in space, but for our simplicity we have chosen alpha axis to be aligned with the A axis, but it is not necessary. If you take the generic mathematical form, you will see that ABC reference axis are here, okay, and there will be another plane. So this is the general linear algebra. If you, so okay, this is one plane in which ABC is there. Now suppose you can have actually another plane which is at an angle, okay, there is an angle between these two, and in this you can define I alpha beta and 0. Okay, so this is a more generic 3 to 3 transformation. Okay, but for our simplicity what we have done is we have chosen A axis and alpha axis to be aligned to each other. Okay, and 0 axis is basically perpendicular to the whole plane, right? So you have this alpha and beta here in the same plane. So this is one plane here, and the 0 is at 90 degrees to the whole plane. Okay, now we are going to introduce something called as DQ0 reference frame. Okay, now suppose we introduce another axis which is called the D axis. Okay, we introduce this thing. This D axis does not coincide with alpha axis. Okay, and now we will start observing the rotating space vector. So suppose let us see this one. Now as I told you, I am introducing a new axis, D axis. Okay, and so this vector is rotating, and I have now introduced a D axis, and suppose I am standing on this D axis and I am going to observe this I vector. Okay, how will it look like and how is the mathematical form of it? Okay, so when an observer is standing on the alpha axis and he is observing the vector, okay, the rotating vector, so we say that I is the rotating vector I am observing from alpha beta 0. Okay, what is this is the magnitude. Okay, this is the magnitude here of the vector, and this is the angular difference between the alpha axis and the instantaneous position of the reference vector. Okay, it is e to the power j theta 1 plus theta. So this is the theta axis and this is the theta 1. These are the two angles here, right? So I am going if I stand on this alpha axis and observe the rotating vector, I will write I alpha beta 0 is magnitude and e to the power of the angle between them. Now suppose I observe this from the D axis. Okay, I am going to observe it from the D axis. Then what will happen? Of course, then the magnitude remains the same. So then I will first write the same space vector as I dq0. Okay, right? Because now I am going to observe from the dq axis. So there is a dq and there is a q axis, which will come. I'll come to it. So I dq0. Okay, the same magnitude. The magnitude remains the same as before, but now you will have this angle, right? Because you have this theta 1 angle there, right? So I can substitute, right? This e to the power j theta, and I can substitute and write it like this, because from here it will come, right? I alpha beta 0 e to the power minus jt, right? Because you can see this quantity, now I am putting it here. Okay, I alpha beta 0 is like this. Okay, e to the power minus j theta by substitution, right? So I dq0, okay, I dq0 is e to the power minus j theta. So I am observing, so this is the d axis, I e to the power minus j theta, I alpha beta, or the other way around, I alpha beta is e to the power j theta into I dq0. Okay, so therefore it shows that a space vector can be observed from different reference frames. Okay, so in case the two reference frames coincide, then this value of theta here is equal to 0. But in case it is not coinciding, which is the case between the, so there is an angle theta between the d axis and the alpha axis, and if you observe the same space vector from the two different axes, what we will see is that the magnitude remains the same, but an additional term of e to the power j theta will come into the expression. This is what is evident from equation number 6. Okay, I alpha beta 0 is e to the power j theta into I dq0, right? Okay, so whatever space vector you are observing from the dq0, you have to multiply by e to the power j theta to understand what are the projections in the alpha beta 0 axis. Okay, now here what is theta? Theta is integral omega dt. Now one thing that now we will introduce is that as we know already that this space vector is rotating at omega speed, but now let me do one thing. I will also say that d axis is rotating at omega speed, okay, at the same speed. It can be also a different speed, of course, it can be a different speed. So yeah, generally you can say that it is omega 0, which is a different speed, but generally omega equal to omega 0 generally. Okay, so in this equation, so therefore what I will say here, so if I take this as omega, so theta is basically integral omega times dt, right? So this theta angle is nothing but integral of omega dt. Okay, now what I am doing here is I am now not only introducing a new axis d axis, so we are going to observe the reference vector from this dq axis, but the other condition is that this dq0 axis is actually rotating with the space vector. Okay, in fact in this case it is rotating at the same speed as the space vector. Okay, so yeah, so this is what, although the dq0 reference frame can rotate at any arbitrary speed, but some specific choices help us in our analysis. In most of the grid connected application, we will set these two velocities of the, so the grid current space vector and the d axis, they are at the rotating at the same speed. Okay, but for electrical machines we can set omega equal to the rotor speed. So if it is a rotor speed, it will be different from the stator or rotor magnetizing flux, so they will be induction machine. In PMSM they will come same at the steady state, but in induction machine the rotor speed and the rotor flux, they are not at the same speed. So therefore this omega and omega naught, so they will be different. But for grid connected applications like our PWM converters, we generally keep omega, this omega and this omega to be same. Okay, so now we are going to so we are standing here, okay, and we are going to observe this current space vector, but now we are going to rotate at the same speed as the current space vector. Okay, so then what will it look like, how will it look like, and this is how it will look like, right? So just so I have stopped the animation for a timing. So now you can see the d axis is rotating here and q axis is rotating, and the resultant space vector is here. The space vector is, that's light blue, but now I am observing from two dq axis which are again rotating at the same speed. So then what will I see? The projection on the d axis is this blue one, this projection will remain constant, and the projection on the q axis, which is the red one, will also remain constant with time. Okay, so then I can see that the dq quantities, when you observe the space vector in alpha beta, you had seen that the projections on the alpha and beta planes were sinusoidal in nature. On the other hand, when you observe the space vector from the dq axis, we see that they have become DC quantities because of our choice of the dq axis. It is rotating at the same speed as the space vector. Obviously, we will see them as a stationary, okay, or as a fixed projection. Right? So this is how it will look like, right? So just to see, coming back, so as I told you here, that I dq0 is e to the power minus j theta into I alpha beta, and again I can then expand the 6 and take the real and imaginary quantities. So id plus j iq. Okay, so we have now dq0 axis. Q axis is leading the d axis by 90 degree, and 0 axis is on the plane which is 90 degree to the dq plane. So for balanced case, expanding 6, what we'll see is this thing, cos theta minus j sin theta into I alpha plus j I beta, and in matrix form you can write id and iq as cos theta and like this, and sin theta by like this. Okay, so this is how it so when you know I alpha beta, you can find out what is id and iq, provided you know the theta. Theta is this angle. Okay, theta is the angle by which the d axis is leading the alpha axis here in this diagram. Okay, so if you again for a more general case, we include the zero sequence component, then I can find out what is idq0 here, given I know what is I alpha beta 0 through this matrix here. Okay, and this matrix is called the TP, okay, Park's transformation matrix. Okay, this matrix converts any three alpha beta 0 variable into a dq0 variable. Okay, you can see here I0 and I0 are the same, okay, in the both the transformations, right? So similarly, we have the inverse Park's transformation matrix, which is I alpha beta 0 TP inverse IDQ0 T, right? So TP inverse will be, you can do this, check this one out, cos theta minus sin theta, like this. It looks like this. You have to do it. Yeah, so this we have already seen, but one of the things that is now becoming evident is that one of the things that becomes evident here is the fact that in when we did the alpha beta 0 transformation, I alpha, I beta and I0, these were all sinusoidal quantities. When we did this dq0, then id iq became DC quantities. Here you can see these are all DC quantities. Now this is one of the biggest advantages of going into this Park's transformation. In Park's transformation, we are going to deal with DC quantities and no longer AC quantities, and actually this helps in the design of controllers. Okay, the controller, if the variables are at DC, okay, this is what we do. If you can recall some of the aspects of controller design, say in DC-DC converters or some, we would like to have DC quantities for controller design, because with the DC quantities you have a very large bandwidth available, okay, for taking any corrective action when you have a disturbance. Okay, the larger is the bandwidth of your controller, the more is the faster is the response. Okay, it is inversely proportional. So we'll talk about it later when we talk about the controller design. But higher bandwidth means there is a lot of frequencies in which your system will respond very fast. Okay, that means your system will respond faster if you have a larger bandwidth. And on the other hand, so it will be very large. Suppose, so if you treat with DC quantities, you have a very large bandwidth available to you. Okay, on the other hand, if you have AC quantities, like in alpha beta transform, you will get I alpha I beta which are at 50 Hertz. Okay, so this is, in order to track these AC quantities, you will need a even bigger bandwidth or a larger bandwidth as compared to a DC quantity. Okay, because you are now going to work with AC quantities, okay, with a certain frequency, 50 hertz in this case. So therefore, the reason why we go for a DQ transformation from alpha beta is to have better controller performance, okay, so that they can operate at DC. Because we got a power expression in alpha beta, we will also get a similar power expression in DQ, and they will come out to be magnitude wise, they must be coming out to be same. That is how we will define our matrices in that way. But the biggest advantage is that in DQ quantities we are getting DC, and that helps in our controller design to a much. So again, you can of course do a direct ABC to DQ transformation, and this is the matrix for that. Okay. Again, as I told you, instantaneous power, you can define instantaneous power PT like this. Okay, now we can do that the same thing. We have already seen 3/2 V alpha I alpha plus V beta I beta, and we can just substitute that V alpha I alpha with VD and ID, and we will get this expression. Similarly, instantaneous reactive power is this one. Okay, so these equations are useful for vector control strategy, both for grid connected as well as motor control strategy. What is vector control? Is that we actually control the active and reactive power orthogonal, I mean, in such a way that they don't affect each other. So we will treat that, okay, the D axis quantities will control the active power, and the Q axis quantities will control the reactive power. Okay, so this orthogonality or the decoupling between the active and reactive power through 290-degree axis, this is achievable with a DQ transformation. We will talk about it later. It will not be evident as at this point of time. Okay, when we do the whole transformation, then it will become evident. Okay, so we are going to take a few examples and we will see how this is going to happen, right? So we will take 3 examples. So this example has 3 parts. This is part 1 here, this is part 2, and this is part 3, and we will apply the ABC to alpha beta to DQ transformation and see how this variables change. Now in this first one, you have, in part 1 we have balanced voltages, as you can see here. We have in second part 2 we have this unbalanced voltages which is coming here, and this is the part 3 which has balanced voltages with harmonics. Okay, so let us expand. That's part 1. Okay, so this is the balanced voltage. So you have a balanced voltages like this which are given by these equations, and of course since it's a balanced case, 0 component will be 0, and V alpha and V beta, you can see here V alpha and V beta, right? V beta is 90-degree lagging, okay, in time, because beta axis is 90-degree leading to alpha axis in space. So V alpha and V beta can be calculated from the Clarke's transformation, and these are the values. V0 equal to 0, and now we have made the DQ axis rotate at omega speed, and it is aligned to the alpha. It is rotating at and therefore in this case we have actually aligned the D axis to the space vector, okay, to the voltage space vector. We have aligned the D axis, so here is the space vector, and the D axis is also on the same thing, so that you have VD as 1, okay, VD is equal to 1 here, okay, but VQ is equal to 0, okay, VQ is 0 here. So which means I have now aligned my D axis, which is exactly at the same speed as the voltage space vector, and they're perfectly aligned with each other. Okay, so this is what is happening, right? Now the second case, okay, unbalanced. So unbalanced, so you can see here we have taken unbalanced voltages. Here you can see 0.5, and so this is an unbalanced voltage. Now we do a alpha beta 0 transformation. What we'll see, of course we will first see that the zero component is no longer zero. Okay, it has a fundamental component omega. Of course we expect that. Why? Because we have you can recall that when you have an unbalanced system, by using the Fortescue's transformation, you can have a positive sequence component, a negative sequence component, and a zero sequence component. So there is a positive sequence space vector, okay, V positive, and then there is a negative sequence space vector V negative, and then there is a zero sequence space vector. Okay, right? So here we can see that the zero component is no longer zero, it has a fundamental component omega. Of course we will see that one. It is a fundamental component. And also the peak of V alpha and V beta are unequal. Why it is unequal? Because if you see this, if you see the space vector, okay, because this is a, this thing here, this thing has, as I told you, it has a positive sequence space vector, negative sequence space vector, and a zero sequence space vector. So if I take the positive and negative sequence space vector, so the positive sequence space vector is having a magnitude, it is rotating like this way, and the negative sequence space vector is something which is this one Vn, and it is rotating the other way. And of course there is a zero sequence, and that zero sequence in the three-dimensional plane which is coming out of the screen. Okay, even if I don't assume the negative, the zero sequence, what is the resultant of these two space vectors? The resultant of these two space vectors is an ellipse. Okay, if you have Vp and Vn, so Vp is going like this, so Vp is a circle. Okay, this is the Vp, positive sequence space vector. Vn is also a circle which is going the other way around. Okay, this is the Vn, and the resultant of Vp and Vn will be an ellipse. And therefore, if it is an ellipse, of course V alpha and V beta will become different, because their projection with an ellipse on the real and imaginary axis will become unequal. In fact, because you have a zero sequence also here, because you have a zero sequence, this is no longer an two-dimensional ellipse, it is a three-dimensional ellipse. Okay, it's an ellipsoid, what I should say. Okay, it's a three-dimensional ellipse which is there. Okay, now what about Vd and Vq? Vd and Vq will contain the double frequency AC component 2 omega. Okay, of course, see, you see here Vd has a average value like this and a double frequency. So this is a 100 hertz or a 2 omega component. This is at if this is at 50 hertz. Okay, I think this is 50 hertz. Okay, sorry, this is not 50 hertz. In fact, this is 25 hertz. We have written it at 25 hertz. We have drawn it at 25 hertz. So this is again, okay, let us put it at omega. So this is omega, then we have 2 omega. Okay, so you can see here that this Vd has a 2 omega ripple. Okay, you can see here that there are two cycles completing here. Okay, for one cycle of Va. So this 2 omega component, why is it coming? Why it is coming? Because if you see now that there are two components, if you see on the Vp and Vn, okay, so you have a positive sequence space vector and you have a negative sequence space vector. The positive sequence space vector is rotating in omega, okay, in this way, and the negative sequence space vector is rotating at omega but the other way around. So if you align your d-axis, here, okay, and your d-axis is also rotating at omega, what will you see? You will see that the positive sequence space vector, right, that is rotating along with you at the same speed. So that part will give you the DC. So the DC quantity here is because of the positive sequence space vector. But the negative sequence, so your d-axis, you are moving with the d-axis like this, but the negative sequence space vector is rotating in the other way. So what will you observe then? The negative sequence space vector, the negative sequence space vector will be at 2 omega speed, because as an observer you are moving at omega speed. The other way is moving at anti-clockwise. So you are moving anti-clockwise, but the negative sequence space vector is moving clockwise at omega speed, and so the relative speed between them is 2 omega, and that is the reason you get this 2 omega coming in the ripple. Okay, its average value will be 0. Okay, similarly you have this VQ and V0 also coming. Then VQ also will have a 2 omega ripple, okay, along with the DC value. Now let us take the third case, balanced with harmonics. So you have this balanced voltages VA, VB, VC, okay, but now I have deliberately introduced a first, fifth and seventh harmonic. Since it is balanced, the first thing that we observe is V0 equal to 0. V0 is 0, V0 is 0 here. But now V alpha and V beta are obtained as balanced, but harmonics are present. And this you can see here, this V alpha and V beta have harmonics, okay. But what is more interesting is VD and VQ has 6th harmonics. Why 6th harmonics are coming? Because of the fact that when you have a first, fifth and seventh harmonics, you see the fundamental, this is the V1, okay, it is rotating at omega speed, right? V5, that is the fifth harmonic space vector, will be rotating at the other, so rotating clockwise. V7 will rotate anti-clockwise again. Why does it happen is because if you see the sine omega t, okay, and fundamental, this is sine omega t minus 120 degree, and this is sine omega t plus 120 degree, right? But for fifth harmonic, this will be sine 5 omega t, and this will be sine 5 omega t minus 120 degree, and this will be sine 5 omega t plus 120 degree. So this value will be sine 5 omega t minus 600 degree, which is equal to plus 120 degree. Okay, so this is VA, VB, VC, and here also VA, VB, VC. But what will happen here is the ABC sequence for the fifth harmonic is opposite to the ABC sequence of the fundamental, and that is why we say that the V5 is rotating at 5 omega speed, but in the other direction. Okay, V7 will rotate at 7 omega speed, but in the anti-clockwise direction. Okay, so this is what we see here. Now suppose your d-axis, you have placed your d-axis here, and it is rotating, you are rotating along with this one at omega speed. What will you observe for the fifth harmonic? The fifth harmonic is rotating clockwise, you are rotating anti-clockwise, so the relative speed between them is 6 omega, and this is what this 6th omega harmonic is there on the d-axis. Similarly, the 7th harmonic and the fundamental omega, they are rotating in the same direction, and their relative speed is 6 omega. So you will get a 6th omega component in the d-axis. Okay, and this is what I wanted to emphasize here, that you have a DC quantity from the d-axis with a 6 omega harmonic or 6 omega ripple on top of it. And quickly we will take two examples which are very simple. Suppose three-phase voltage and current are given by these expressions VA, VB, VC, IA, IB, IC. What is the magnitude of the instantaneous active power in watt, okay, in the alpha beta, and what is the magnitude of instantaneous reactive power in var? Okay, so we use voltage invariant transformation. This is just straightforward application of the matrix, but you can as well write it straight away because we have used magnitude invariant transformation. So which means that this 200 will remain 200, okay, and so this will be V alpha will be 200 sin omega t. So V alpha and VA will become same, identical. Okay, you see here VA and V alpha become identical, right? Same magnitude, and alpha axis is coinciding with A axis. Beta, V beta is minus 200 cos omega t. Okay, it is lagging the alpha axis, okay, in time. So V beta is minus 200 cos omega t. And similarly, I alpha and I beta can also be found out, right? And once you get this one, you can just simply put into this equation of PT and QT, and you will get 3000 watt and 5196 var. In fact, since this is a balanced case, this will be equal to 3 VRMS IRMS cos phi, and this will be 3 VRMS IRMS sin phi. Okay, numerically they are all equal. You can check it out yourself. Another example, quick short example. Consider the grid current expressed in DQ frame as IGD is this much, IGQ this much. What is the RMS magnitude of the per phase grid current? RMS magnitude will be same, okay, root over of 9. So this is, sorry, root over of 95 square plus 55 square. Okay, these are the IGD square plus IG square and divided by root 2, because when you do the DQ to ABC to DQ or some like that, okay, you get the, when you talk about space vector, you get the peak value. Okay, so RMS you will get by 1 by root 2. So the answer is 77 ampere. The last example here is this one. Suppose you have a grid connected VSC. The grid voltage space vector magnitude is 220 volt at an angle of 300. So this is your grid voltage. Okay, this is the grid voltage space vector 220 at an angle 30 degree. The current supplied by the grid are given by ID is this much and IQ is this much. Okay, so what is the three-phase active power and what is the three-phase reactive power supplied by the grid? Very simple, straightforward. So PT is 3 by 2 into VDID plus VQIQ, right? And you can find it out. This 3 by 2 is coming here, and you can substitute the VD value of VD. This is VD, this is ID, VQ, IQ, and this will be minus 3276 watt. In a similar way, you can do the QT, right? 3 by 2 VQ ID minus VD IQ, and therefore when you put these values here, you will get 395 watt. Okay, so you can just do these exercises yourself. So with this, actually, so today we covered the Clarke and Park transformation, and we found out how you can calculate the powers with the help of Clarke and Park transformation, and more importantly, why we moved from ABC, from a three-phase quantities to a two-phase quantities. ABC to either alpha beta is the Clarke's transformation, ABC to alpha beta and subsequently DQ is the Park's transformation. There are basically two benefits of going into from three-phase to two-phase. First benefit is that when we use the two-phase quantities, we will independently control the active and reactive power. Okay, this will get evident after some lectures where we will find out the expressions of the power when we use vector control of the grid connected converter. There you will see that the D axis is exclusively used for controlling active power. The Q axis quantities are exclusively used for reactive power control. So this is one advantage. The other advantage of using this transformation is that the performance of the controller improves, because suppose you go to the DQ domain, your quantities become all DC, and it is much easier to develop controllers with when you talk or when you deal with DC quantities. Okay, and so with this we conclude today's lecture.